Thank you very much. I would like to thank the organizers for giving me an opportunity to attend this excellent conference. This concerns double Bayer decay only in the second part of my talk. I'm going to talk about some work we did in the recent past, experimental work that were relevant, that could be considered relevant for benchmarking aspects of weak interaction physics using single Bayer decay and two-nucleon transfer experiments. Just a quick overview. We know that the weak interaction is chiral in nature. There's only left-handed neutrinos, there's only left-handed weak interactions, and this is embedded in the larger framework of the standard model. But since the 70s, there has been an interest in restoring parity as a good symmetry at a higher energy scale, and there have been several extensions offered to this model that are left-right symmetric that allow the existence of right-handed weak interactions. And these are appealing not just because they restore parity at a higher energy scale, but also because they allow the existence of right-handed gauge bosons that could be explained, that offered explanations for the smallness of neutrino masses and the observed CP violation. And these have been refined over the years by various authors. And as Fedor said yesterday, there is a direct connection between right-handed weak interactions and neutrinoless double Bayer decays. This is an incomplete list of people who have worked in this field. So how do you probe for right-handed currents using atomic nuclei? In the 70s, again, Holstein and Triemann expressed the right-handed coupling constants, a relation that would relate the right-handed coupling constants to observables by looking at beta decay of spin-polarized nuclei in terms of these spectral functions that are combinations of the axial vector, vector form factors, and leading order terms. And if you see here, if you this is a very recent experiment from Triumph that has set the most stringent limits on right-handed currents. The spin-polarized potassium-37 looked at the beta asymmetry, which is essentially the ratio of F4 to F1. The presence of new physics, of right-handed physics, modifies these spectral functions in such a way and is parameterized in terms of these deltas and the zetas. Delta is the mass ratio of the right-handed and the left-handed boson, and the zeta is the left-right mixing angle. So this is a table, this is some work done in the 90s in which they looked at all the nuclei that can be used for such studies. And you can see here is potassium-37, which has set the most stringent limits thus far. What I've highlighted is neon-19. If you notice here, neon-19 has the smallest beta asymmetry ever predicted and measured. It's 0.3%, it's 3%, 0.03, and this offers maximal sensitivity to right-handed physics. The sensitivity of neon-19 Bayer decay experiments is more than 60 times that of potassium-37. And this is primarily because the leading order vector and axial vector form factors cancel. Such a cancellation doesn't exist in the right-handed sector. So this makes it small and highly sensitive. So the idea is to spin polarize the nucleus, measure the beta asymmetry, which is here, and then set exclusion plots for new physics. This beta asymmetry has been measured several times in the recent past. The last measurement was done in 1996. You can see here there have been two kinds of measurements. One is the beta asymmetry at zero kinetic energy, and one is the total integrated beta asymmetry. This was done because these people were looking for second-class currents. And to unify these two results, what I did was I extracted the value of C, the axial vector form factor, from these measurements, and you can see they have been mostly consistent with one another. Now, the idea is to look for the standard model prediction of this and see if there is an agreement. So if you want to set meaningful bounds on the right-handed physics, you not only need the beta asymmetry term, but you need to find C, the standard model prediction of C, which also can get modified by these X and Y parameters, which can be obtained by the FT value for 0 plus to 0 plus super allowed decays to that of neon-19. This FT value is corrected for small effects of isospin breaking and radiative corrections. So the idea is to measure this super allowed 1/2 plus to 1/2 plus beta decay with very high precision by measuring these weak branches. This is the forbidden branch and this is a suppressed branch. And then you take the ratio of this, take the measured value, and do set bounds. Another interesting part is, although the weak interaction has been extensively studied over the past several decades, the neutral current sector of the weak interaction is not very well known. That is because of, it's a decay of quarks in a strongly interacting gluon field, and there's a non-perturbative QCD that comes into play. So the idea is, there has been proposed, is to use parity violation as a filter to isolate these weak interaction effects. So in the 80s, there was a model proposed, a phenomenological model proposed by Deplanck, Donoghue, and Holstein, which used a meson exchange model. They don't talk about quark-quark weak interactions, but they talk about nucleon-nucleon weak interactions with a strong vertex and a weak vertex that's explained by the exchange of these mesons. And these are related to the observables, the parity violating observables, and the understanding was that this was dominated by only the isovector part of the current, which in turn is dominated by pion exchange. And the idea was to study hadronic weak interactions this way by looking at longitudinal asymmetries in scattering experiments and in gamma ray measurements. This field went kind of dead in the 80s. There were no really observations. There were observations that were consistent with zero, and nothing really happened. But it kind of got revived in the recent past by a lot of development in theory that have indicated that this emphasis on the fact that the hadronic weak interactions are dominated by pion exchange in the isovector component is kind of misdirected. And you should be looking at isoscalar and isotensor components. However, these experiments are hard. The latest experiment, there's a review on this by Gardner, Haxton, and Holstein. But the latest experiment was the NPD gamma experiment, which also measured a very small null result for the pion coupling constant. The challenge here is that your weak interaction effects are dwarfed by the very strong interaction effects. And you're looking for a signal that's of the order of 10 to the minus 7. However, Wick-Haxton and collaborators identified that you could use parity mixing in closely spaced doublets in light nuclei to use that as an amplifier for your signal. So there's simple two-state mixing between two opposite parity space states that are spin parity states that are close to one another. The nearest one is really far away, and there's an enhancement because of isospin mixing, and an additional enhancement because you have M1 and E1, magnetic dipole and electric dipole transitions interfering with one another. And you measure the gamma asymmetry from a spin polarized nucleus in fluorine 19, you see here it's more than 10 orders of magnitude higher than 10 to the minus 7. The problem is, how well do you know the matrix element? How well do you know the wave functions? So when Wick-Haxton did these calculations, he did it for fluorine 18 because they were looking for purely the isovector component, which was dominated by pion exchange. And he said that if you look at the beta decay of the isobaric analog state in neon 18 of this 0+ state, and you look at the forbidden transition from the 0+ to the 0-, and you measure that very accurately, and you calculate the ratios of the matrix elements, all the systematic effects in the calculations will cancel out, and you agree to within 5% to whichever calculation you do. A similar analysis was proposed for fluorine 19, which is now being suggested to be reinvestigated, but we don't know if such a calculation can be done, such a trick can be used, because this has both isoscalar and isovector contributions because it's a T-half to T-half transition. So we need a high precision measurement of the branching ratios. So we did an experiment at Triumph in which we took neon 19 beam, implanted into the now decommissioned 8-pi spectrometer, and implanted onto a tape, observed the decay, measured the half-life with multi-channel scalars, and we found a huge model dependence depending on what dead time you use. The idea is to put self-imposed dead times onto the data acquisition system, correct for it because you do it very accurately, and we found out that these scintillators that we were using for the half-life measurement had this after pulsing that needed to be corrected for. that was corrected for, and now the half-life is known with 0.01% relative uncertainty. For the branching ratio, you look at the gamma rays, but there are hardly any gamma rays because most of it goes to the ground state. They're just these weak gamma rays, so it's looking for a needle in a haystack. But we had these Compton-suppressed germanium detectors, as a result of which we could identify the two weak transitions, and a whole bunch of corrections come into play because of coincident summing, pile-up, and so on and so forth. And after doing all these corrections, we find that we can measure the first forbidden beta decay to better than 3 times precision. So now the super allowed branch is known with that much precision. The precision in FT value was improved by a factor of 3.5. How does this affect things? This tells you that the standard model prediction for the axial vector form factor doesn't agree with all these measurements. You can rule out these 3 because it violates CKM unitarity by more than 5 sigma. You can rule out this one because it again violates CKM unitarity. You're only left with this 1975 measurement. These are the exclusion plots on right-handed currents at 90% confidence level, plotted by this Triumph paper. These are new exclusion plots using Calaprice's data and our measurements. We see that you can exclude, now we can exclude everything here in the left-right mixing angle and a lot of it here. So now we have one of the most precisely measured FT values in t equal to half mirror beta decays, and the first forbidden beta decay rate is found to be 10 times lower than the shell model calculations by Wick, Haxton et al. That needs to be investigated. So now there are calculations underway to investigate this further. He's on it with his collaborators, and remeasurements of both the beta and the gamma asymmetry measurements are welcome. Now, I'm going to move to the second part of my talk. Like I said, there exists a direct connection between right-handed currents and double beta decay. It was explained by nicely. Some aspects of it were discussed by Fedor yesterday. So I'm going to move to our 2-neutron transfer experiments that are relevant for benchmarking aspects of neutrinoless double beta decay in 136 xenon. So here, I'm not going to get into this too much because everybody knows about it, but the idea, the takeaway point is you want to get somewhere here in the next generation experiments, and the challenge is to reducing this band of uncertainty that arises from the matrix element evaluations. There are certain advantages for 136 xenon double beta decay that has been discussed by Giorgio. I'm not going to get into that too much, but it's interesting to note that 136 xenon is a singly closed shell nucleus and nearly spherical with n equal to 82. Okay? So these are the calculations for the nuclear matrix element for 136 xenon double beta decay. And you can see here, like John mentioned, there are these really big values from this non-relativistic EDF and the CDFT calculations, and the calculations get smaller and smaller. As you make the calculations more and more sophisticated, the matrix element gets smaller and smaller. It's interesting to note that there have been recent calculations by John and by people in China in which they use deformed QRPA calculations, which give much smaller results than the spherical QRPA calculations. And the explanation for this is that n equal to 82 has a very sharp Fermi surface, so this curtails the overlap between the wave functions. There's an attenuation factor of 2, which is evident here. Also, this shell model calculation used only 5 orbital valence space, is a 5 orbital valence space calculation, and this one used 7 orbitals. So as you make it more and more sophisticated, the matrix element gets smaller and smaller. Nonetheless, there used to be a factor of 2 point something discrepancy before. Now there's a factor of 4.2 discrepancy. So how do you investigate this? One aspect of the QRPA calculations is that the pairing correlations between like nucleons are approximated using BCS correlated pairs of protons and neutrons, which are distributed in a Fermi surface like this, smooth occupancies. And this approximation is very critical for the QRPA calculations. However, it's known that near closed shells, this approximation is not valid, and it can be investigated. This is mentioned in this very nice review article, can be investigated by 2-nucleon transfer reactions in which you would see, if BCS were a good approximation, you'd see a strong population of the 0+ to 0+ ground states, but if the approximation breaks down, so-called pairing vibrational states in the vicinity of shell closures, you'll see a large population of the excited 0+ states in these two nucleon transfer reactions. So the anatomy, this was again discussed by Otsuka-san, so I'm not going to get into too much details, but both the QRPA and the shell model calculations have a common theme. They're dominated by the decay of pairs that couple to 0+, and their cancellations from the other terms dominated by the 2+. So you can disentangle the two contributions. There was a recent paper by Alex Brown and collaborators which showed that you can also do calculations as sums of products over intermediate states by going for germanium 76 from selenium 76 by going from germanium 76 to 74 to 76. So 2 neutron removal, 2 proton addition in terms of these 2 nucleon transfer amplitudes. Okay? And this directly, the important factor of this calculations is that it directly relates to pair transfer properties of the ground states that can be probed experimentally by PT and helium-3N kind of reactions. So we did an experiment to benchmark these calculations using the 138 PT reaction, which is a 2 neutron removal from 138 barium, which is also a singly closed shell nucleus N = 82, goes to 136 barium, which is the daughter for neutrinoless double Bayer decay. This was done in the Q3D spectrograph in Garching, which is, the lab is now shut down since December, unfortunately. And it's a high resolution momentum spectrograph that you can, allows you to identify your reaction products by delta E, E, and E arrangement of detectors at the focal plane. So these are a spectra for 138 barium PT. We see a lot of 0+ states that were not observed before. These are the angular distributions of all the 0+ states that we observed. In black are the 0+ states that are labeled, that were known from before, listed on NNDC. The red ones are the new 0+ states. We did a careful analysis of the optical model parameters, used the reaction data. Francesco, this was for you. And you can see here we chose the right optical model. And then we see this huge fragmentation of the L = 0 strength to these two states, around 30%. And the total fragmentation is distributed to 50% of the ground state, which is a great big breakdown of the BCS approximation. Then we collaborated with Alex Brown to use the new shell X code to get the wave functions for 138 barium and the first 50 0+ states in 136 barium, and also calculated the 2 neutron transfer amplitudes using both direct and sequential transfer. And what we observe, this is a running sum of the cross-section, L = 0 cross-section at the most forward angle, and he used 3 Hamiltonians that he commonly uses for neutrinoless double Bayer decay matrix element calculations, and we see an underestimation of the cross-section by a factor of 2. This is again work done by Alex Brown and collaborators in the 70s, in which he observed that you need corrections to the 2 neutron amplitude files in his shell model code from a perturbative calculation that allows for contributions of physics effects much beyond the model space. And if you do that, the pairing interaction enhances the J = 0 contributions, and it enhances the PT cross-section. So he did that. He used the corrected TNA file, and now the agreement between all 3 of them and the data is within 15%. So he used 23 orbitals beyond the model space. He could have used more, depending on computational power. Now the takeaway point is that 136 xenon, remember he goes from 136 xenon to 134 xenon to 136 barium. 2 neutron removal, 2 proton addition. This transition is very similar to what we studied, because both go from a nuclear structure perspective, because both go from N = 82 to N = 80. So he used similar corrections for his matrix element calculations. These are, how much time do I have, Tony? I'm doing well? Okay, good. So just a quick overview of the results. This is what we also collaborated with QRPA theorists and Horoi, who also does shell model calculations. So a quick overview of the results. In the old days, Fedor and collaborators in 2013 used a QRPA calculation with 23 orbitals and got the gamma of Teller part of the matrix element to be 2.18. We increased it to 5 orbitals. Again, when you make it more sophisticated, the matrix element reduces. And but in this case, we disassembled the j equal to 0 and the j not equal to 0 contributions to see how much each is, and then kept that number for comparison with what we get from our experiment. Again, for old shell model calculation by Javier and collaborators, gave a number that's this, but they also disassembled, disentangled both contributions of j equal to 0 and j greater than 0. And Horoi redid the calculations with the new Hamiltonian, and it's interesting to see that his result agrees very nicely with the QRPA, almost exactly. Then we used Alex Brown's calculations to see how much this MGT would be without the TNA corrections for core polarization from orbitals beyond the model space. And he gets 5.72, which again reasonably agrees here and exactly agrees here, strangely. And then he included the core polarization corrections to the 2 neutron amplitudes, and he gets 9.04, which is a ratio of 1.58. If you multiply this ratio with 5.67, you get 8.96, which very nicely agrees with 9.63. Previously, you had these numbers to compare with. Of course, as Otsuka-san mentioned, the core polarization effects, the effects from higher orbitals, will also increase the negative part, the part that cancels this, but it's not clear if it's going to be it's going to cancel out evenly and give the same matrix element. So, but the takeaway point is this was based on a comparison with our experimental data. In conclusions, our work shows that there's a large breakdown of the BCS pairing approximation for neutrons in 136 barium. We did a similar analysis with using 136 barium as a target, and we see that this persists with 134 barium. This is explained in Jesper Once's poster, and it's quite likely that there's a change in deformation between 138 to 136 to 134 and so on and so forth. And this is important because 138 is singly closed shell, just like 136. So there are changes in deformation, and it's known that barium nuclei with n less than equal to 82 are shape transitional. So there are deformation effects that need to be taken into consideration in future matrix element calculations. And most importantly, our analysis that takes into account, or Alex Brown's analysis, that takes into account core polarization corrections to the TNA results in the value of this j equal to 0 part of this matrix element that agrees with a large model space QRPA. The takeaway point is we think that we got a way to benchmark future calculations, especially the j equal to 0 part, with actual nuclear reaction data such as PT, helium-3N, 0, 1, good. But I want to highlight that there was this paper by Jason and John who used many-body perturbation theory treatment to see how much the contribution is exactly from physics effects beyond the model space. And they observed that for germanium-76, there's approximately 20% enhancement in the value of the matrix element. For selenium-82, it was roughly 30%, if I'm not wrong. And we would recommend that you do similar calculations for 136 xenon, which Jason said are possible, to see if actually we're on the right track. And this will definitely benchmark the large j equal to 0 contribution to the matrix element and give us additional information of how much the cancellation actually is. I think, so that's the collaboration of people who are involved in this work. People highlighted in red are the PhD and master students who analyzed the data, and theory came from Brown, Horoi, and Fang. Thank you very much.